My name is Mohammad Atikul Islam Atik, ID 1706118. Today's our project is car speed control with BLDC motor. We can see the summation part here, the input curve and measured speed. We use it to minimize the error and feed it to the PID controller. The minimized error is goes to the buck converter. Uh, Buck converter works with basically takes input of 100 volts and used to switches as switch 1 and switch 2. This by switching them on off, we adjust the DC adjust it to different DC voltage level, and according to which the BLDC speed control will works. And then this different DC voltage level is fed to the three-phase converter, and then three-phase converter will work according to this.
My name is Rasin Mohammad Ihtemam, ID 1706117. The three-phase inverter takes DC voltage input from the buck converter and energizes the required phases of the brushless DC motor stator. And which phases to energize the three-phase inverter takes this command from the computation logic. Here in this block we can see that the switching pattern from the computation logic is fed to the in three-phase inverter, and DC supply is fed from the buck converter. Then the three-phase inverter energizes the phases accordingly. Say for example, when the rotor of the BLDC is between phases B and C, and the rotor north pole is between phases B and C, the sensor block senses this position of the north pole and gives command to the commutation logic, and commutation logic gives command to the three-phase inverter, for which the B phase is energized in such a way that there is a north pole, and C phase there is a south pole. The A phase does not have any electrical energy at that moment, and as a reason the north pole of the rotor comes close to the C phase, and when it crosses over the C phase, the B phase is cut off from the supply with the three-phase inverter, and the three-phase inverter energizes A in such a way that there is a magnetic south pole, and in C there is a magnetic north pole. For the reason the north pole of the rotor try to reach the A phase, and thus the three-phase inverter gives DC voltage to required phases of the three-phase BLDC.
Hi, I am Sakib Shahriar, ID 1706113. Here, the sensor is connected to the rotor and the sensor will work according to our commutation logic. There are 6 cases in our commutation logic. Note that each time only one of the outputs will be positive and the rest will be 0. Say for example, when the rotor is between 0 to 60 degree, the sensor will command the commutation logic to activate the switching pattern 1, and the other patterns will not be activated. In switching pattern 1, only A and C phases will be activated. Then when the rotor is between 60 to 120 degree, the commutation logic will activate the pattern 2, and here according to our logic, A phases will be cut off here and B and the C phases will be activated here, and vice versa. Again, thus they work together to give the exact switching pattern or command to the inverter. The sensor here is Hall effect sensor named.
My name is Rony Barman and ID 1706114. So the rotor of the BLDC motor is connected to the shaft or axis of the rear tires through the gearbox and differential. Now here is the vehicle body where rear tires and front tires are connected. So in the vehicle body we see some different parameters, and we can choose like mass of the vehicle 30 kg, then frontal area 0.04, drag coefficient 0.1, air density 1.18 kg per meter cube. Now, the output side, we can measure the vehicle velocity along with the input velocity that we are controlling to its acceleration and brake, which is simulated by a slider.
Okay, it's time to check the output of our model. So let's just run our model. I'm going to change the acceleration, input acceleration in the slide again. It is in kilometer per hour. So our model ran perfectly. Let's check out the output of our model. So there is two graphs. First one is the blue one, which is the desired speed, and the second one is the yellow one, which is the obtained speed by our vehicle. Our vehicle trying to match the desired speed, but it didn't follow it perfectly due to inertia and rolling resistance. Now just integrate our speed and we will get the distance, which is nearly 0.038 kilometer. Let's open Data Inspector. First one, we can see the DC source voltage, which is here. Our buck converter adjusts the DC source voltage to modulated DC voltage to get different speed, and the modulated DC voltage is here. Let's check out the measured speed from our BLDC motor. If we check out the measured speed, we can see the highest speed is 1200 RPM. So this is the output of our model.
Hello, this is Fahim abid Arnob, student ID 1706115. This is the actual vehicle model with a normal DC motor. Here we have a specified drive cycle and a longitudinal driver as PI controller. Here we can observe the speed output, which we can see our vehicle was closely trying to follow. This part monitors the charging and discharging of the battery and records it. We can see the battery has discharged from 90% to approximately 55% at the end of the graph. But we can see some spikes here. It is because of the regenerative brake. When the driver brakes, the motor of the car acts as a generator and produces electricity to recharge the battery. As an end node, we couldn't connect a single-phase lithium-ion battery to the three-phase stator of the previously mentioned BLDC motor, so that part is absent there. Thank you.